Machine learning image recognition. We're going to teach an AI how to, well, a bunch of matrices. We're going to teach it how to recognize pictures, and in this case numbers, which is like a hello world program for beginners, is to learn how to use image detection. In this case, just simple numbers like text. We're gonna handwritten text with numbers 0 to 1. This is the MNIST. As we're training AI models, we're essentially just dealing with matrices. This whole time, just picture a matrix, which is a bunch of numbers, in this case floating point values, and they're typically aligned in a grid pattern. Taking a look here, the typical matrix that we're looking at are these kinds of things right here. Check this out. We have a 3 by 3 matrix, and that's what we're doing the whole time. Everything involving the AI approach is going to be involving a matrix, whether we're doing image recognition, image processing, image generation, text processing, text generation. It's all to do, it's all of its matrices. And so when we take that organic information that's usually like text or images, we need to convert it into a format that is a matrix. And then we can perform mathematical computations to multiply those matrices together, and also do other fun things to be able to to train an AI so that it understands it's basically an optimization function. We're optimizing for the AI to understand or learn something. It doesn't necessarily understand, it's just able to identify patterns. And it's very satisfying because we would be able to train a model with a whole bunch of input data and then feed it additional future data, and it's going to be able to get us really close to the right answer. And it's a lot more efficient and powerful, and sometimes more accurate than having a human do it. So that's why AI is so powerful. Let's create an AI model that's able to detect images of numbers, of handwritten numbers. This is one of the Hello World programs that usually comes with most AI frameworks, machine learning frameworks, that you can take an input image of a bunch of handwritten characters and then train an AI model to detect them. This is the MNIST dataset. And it kind of looks like this. Most typical models, you'll be using something called a convolutional, the conv layer, a pooling layer, and then you will use a fully connected layer. There might be some dropout. There's also a flattening aspect, but there's really only these two layers, the two convolutional layers. That's where the model weights will exist. Everything else that you see in here is in addition to the fully connected layer. That's where all of the intelligence lives. So let's walk through part of the program for the Hello World of the MNIST dataset. We're using Keras and NumPy. We will be importing some of the capabilities that Keras gives us for free. Some of these algorithms are very satisfying because then we don't have to write the for loops and the algorithms ourselves. So this helps a lot. And all these things are going to allow us to manipulate the matrices. Input is going to be describing the input shape of our matrix for the input model. So if we have a 28 by 28 resolution image, in this case, with a color channel of 1, that will describe the input shape. Dense is just a standard matrix. It's a simple X by X matrix, and it can be any shape or size that you want. Flatten is a sort of a helper function that will convert the dimensionality into something that will fit a dense matrix. So convolutional networks usually like to have 3-dimensional inputs or data in each input, which allows it to have multiple channels of data, such as varieties of colors like red, green, blue, alpha, and maybe even a few other things. You could have other things in there. Like infrared and x-rays. Oh, there we go. We can have all sorts of spectrums in there that you can the number of channels, you can have a lot. In the conv2D, the convolutional network, this will be where the layer weights exists for the most part, in addition to the dense layer. So the dense layer and the conv layer are gonna be where our layer weights exist. Max pooling is gonna help us reduce in that model chain, it's gonna reduce the overall number of parameters by selecting the highest values. That's it, that's all it does. It takes an input matrix and it's like, okay, it does a few extra things. It's gonna look in a series of steps, we'll walk through this, over the matrix, and it's gonna select the highest values. That's really what it does. And dropout is another algorithm that selectively forgets data. And that's literally all it does. From a random perspective, choose a random number of weights to be completely forgotten. And that's only used during training time. The number of classes that we have in this case is 0 to 9, which is a number of digits. So we're going to have a whole bunch of images, in this case like around 60, 70,000 images that we're going to be training our data set on. That's what the MNIST data set has. It's a lot of data, it's a lot of images. And each of those images is going to either be a digit between 0 and 9. So that's 10 possible outcomes. Our input shape is going to be the resolution of every single one of those pictures. In this case, it's 28 by 28 and by 1, which is we're going to have a gradient between 0 and 1. So it's a non-color image, grayscale image in this case. Then we're going to load our training data set here, and it's also nicely parsed up for us. They give us our test data and our training data. And in each of these parentheses is going to be just a segment of the overall population of the data. So I believe it's the majority of the data is going to be training data, so about 60,000, and then the rest is going to be 10,000 samples, 10,000 images, and we're going to separate those into our training and test data. Now, what does this look like? What does it actually look like? So the Y data is going to be the output or the labels, right? So it's going to say, oh, this is a 0, this is a 1, this is a 9, this is a 7. That's the output data, the Y. The same here. They're the same thing. It's just data is split up so that way we can test to see if the AI was trained well enough to see if it has data that it's never seen before, if it can accurately identify an image, for example. So what does this look like? What is in this training data right here? I'm very curious. So what we can do is we can take a peek inside there and then print on the screen, because this data is going to be a value between 0 and 255 for every single pixel. So this is essentially the pixel data right here, 28 by 28. And so what I'm going to do is I'm going to loop through all of those pixels, 28 by 28, and I'm going to print out the third image essentially. If there's any pixel data there, I'm going to print out a block. Otherwise, it's going to print out a space. And this is what that looks like. So we have here, we've got a number. It looks like a number 2. So in this case, it's a number 2. It's a pretty straightforward. And so if I printed out more of those, we'll see a variety number of numbers. And if we take a look at what the actual matrix is itself, it looks kind of like this. No, it looks exactly like this. This is the matrix. Well, that's the matrix after we've applied a division of 255, which is the max value. So it's going to convert the data into a floating point number between 0 and 1. So these values here are going to be really, really close to 255 because they are right at the top there. So that's our training data. That's the 70,000 images that look like a bunch of numbers. And here's the great part about the MNIST. They've done a lot of the heavy lifting for you. They've taken the images and they've in that 28 by 28 grid, they've moved the numbers around a little bit. They've done a little bit of rotation. They've done a little bit extra work for you. So that way, when you train a model, it's going to be able to learn those numbers a lot better. That's why the MNIST training data set is so important from a getting started perspective, because we get to learn just how the AI models work in general. We don't have to worry about extra techniques to manipulate the input data, so that way we get a model that learns more on the outside. When we're training an AI model to learn image recognition, we'll be using a sequential model that is usually a convolutional neural network. This convolutional, it's a CNN, is a set of patterns that we can apply to matrix operations that are more effective with two-dimensional data. Because in an image world, we have, usually it's going to be a two-dimensional, right? It's a picture with a bunch of pixels in a certain shape. And with a convolutional neural network, we're going to be able to take advantage of that grid, look at the proximity of data between each of the pixels. So we can see here that our image and the number 2, you can see it's got a bunch of pixels, and some of them are activated and some of them are not. What we want to do with that grid is sort of detect the features based on the proximity of the pixels in both directions. This is the difference between a normal feed-forward neural network model and a convolutional model, is we're going to take the proximity or the adjacent pixels and create a relationship between them by doing math between them. It's going to look something like this. Check this out. We're going to take a convolutional, so right here, if we zoom in a little bit, this block right here, each of these horizontal layers here, or these vertical layers here, so you've got an image here at the front, Right behind that is another image, and behind that's another image, and behind this is a batch. And what we're going to do is we're going to capture the output by multiplying the adjacent pixels together in usually a 3x3. And a 3x3 is an industry standard for pixels. We've done many tests over the years to find which of the, like, what if we increase that size to a 5x5 or a 10x10, right? It seems like we're covering more space, so there should be a better output. However, typically in most scenarios, a 3x3 actually performs a lot better. So we can just think of it as looking at all like a grid, like the 9 pixels that are next to each other. And in a convolutional neural network, the pixels in that 9x9 grid, and you can see that we're like sort of zooming through each of them in a stride of 1 by 1. And then for each of these colors, they're essentially its own dense matrix. Each of those is an independent dense matrix. And they're all going to be initialized with random values at the beginning. And so we take each of these dense matrices, which are called the filters. I don't know why they call them the filters. I mean, I'm pretty sure there's a good reason, but they're just a matrix with random values. Each one has random values. And we're going to multiply the output directly against that matrix, and then we're going to, based on the number of features, we're going to have a shape that looks like this, and that's the output. So each of these bricks here, those are going to be the features, or no, not the feature, they're going to be the weights, the layer weights. This is the thing that the model will remember. These are the things that we're going to optimize during back propagation, optimizing these layers here. It's the only thing that we really want to keep that we're going to be saving. So this is the inside of a convolutional neural network. It's these things right here. And this is just one layer. Taking a look at it here, we have 1, 2, 3, 4, 5, 6, 7, 8. So this is an 8 filter 3x3. So the kernel size is 3x3, and there's 8 filters. But really, they're just these matrices. They're just... Then we're going to take the output here, and then we're going to run it through another layer. So that looks like this. Here we go. Let's check this out. Each of these blocks here are going to be what we saw as those bricks. Each of these squares is going to be one of those bricks. We're going to pipe the original number 2 into the brick based on the kernel size, and it's going to output different, essentially, features, right? So it's going to take the data and it's going to create identifications, usually by finding the edges. So you can see here in this first column, the second column here, this is going to be the feature detection. And then it goes to the next layer, which is the pooling layer, which is just an algorithm. It's just a reduction step. There are no layer weights. There's no real matrices there. It's just a reduction step. So there's no intelligence there other than, for the most part, you're going to be usually selecting the maximum values. So you can see all the highlights here. We're going to do the best we can to select the highlights. So you can see a lot more of the bright areas are being kept in this case. So that's what a pooling is. It's a reduction. We're going to take the information that we learned from each of the filters in the convolutional layer, and then we're going to be reducing it. And that kind of looks like this. So say, for example, we have a simple 3x3 matrix here, which like is an image. Pretend it's an image, right? So that's our image. It has 9 pixels. Then we make sure to shape it in the way that convolutional matrices they like it to have an extra parameter for channel, right? So colors and other inputs, and then we're going to throw it into a pooling layer, and in this case it's a max pooling layer. And a max pooling layer, it's going to be based on the pool size. It's going to capture the window of the highest values, and you can see the output is going to be 5, 6, and 8, 9. It's just a simple algorithm. It just looks across. It's the same as the conv network when the convolutional layer, when it's going through each of the adjacent pixels, and it's gonna capture a set of output, and it's only gonna give you the maximum values. That's it. It's really simple. And then you repeat that process a few times. So we start with our raw input data. We do matrix multiplications using just the window size, or the kernel size, to snapshot the inputs to find relationships between all the pixels, basically. Each of these are going to have, well, the internal weights here for the conv network are going to be randomly initialized, and then it's going to pipe that over to a pooling layer. The pooling layer, which is basically is an algorithm that will reduce it, finding the brightest values. Then we're going to do it again. Another conv network over to a pooling layer again, which is the same thing. Then we flatten it, and then we pipe it into a dense layer, and then we have the output, which gives you the answer. And as you can see here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 0 through 9, and it's going to tell you that 0, 1, 2 is the the answer. So that's why this pixel is bright right here, because it's the number 2. Now this is a pre-trained model, so that's why all of this shows up as is. If we were to visualize an untrained model, all this would be just fuzzy data. It would just all look fuzzy. So here's what it looks like end to end. Raw data input, compare adjacent pixels, reduce that, compare adjacent pixels again, reduce it again, flatten it, and then one more matrix multiplication to get the output. And then we could do a softmax. That's usually a softmax output there. Or you just find the largest value. Now here's the cool part. You can do this with any kind of image. It doesn't have to be numbers. You can do it with like aerial photographs. And we're taking a bunch of pictures of the forest and we're looking for something that's not a tree, right? We're like, oh, there's a house right there. Is there supposed to be a house right there? Or we're looking for, say, a missing person. Zoom over an area and just have a bunch of drones take pictures, and then we can input all those pictures into a model, and then can find things that are like most likely not to be belonging inside of a nature. Like, oh, there's a tent, or there's a person, or there's a fire, which is great because now the computer can do all the work and a human doesn't have to look at any of the images. So that's why machine learning with image recognition is so powerful. Building an image recognition machine learning model is actually fairly straightforward when we're using Keras. After you've collected all of your input data and converted it into a shape that the model will enjoy, where it'll be compatible with, then we can start training the model. So we have here some Python code where we've loaded the MNIST data set, because what we're gonna do is some image character recognition. Is it a 0, 1, 2, 3, all the way up to 9 digits, right? Actually, it's 10 digits, right? Because 0 counts as a digit. So we've got our training data here, and it's gonna be image data, which is gonna be a bunch of numbers. This is an example of one of them. It looks like, you know, the number 2 in that case. We're gonna train a model to detect what number it is. We already have all the images and all the labels, basically saying, this is an image of a number 9, this is the image of a number 7, and we have a lot of examples for the model to learn from. So we're gonna update that a little bit by converting the data into a floating point value between 0 and 1. Since our data is grayscale, it's going to give us a value. The training data is in a value of 0 to 255. But what we want to do is put it into a floating point number, so that way we can better learn without having any vanishing gradient problems. So we're going to divide that by 255, and then we're going to change the shape by adding a dimension. And in this case, we only have one color channel, right? It's a grayscale between 0 and 1 in this case now. So here is what that data looks like when we've converted it to floating point numbered between 0 and 1. We've got all these color values here. And then we're gonna convert that into a shape that convolutional neural networks like, which is this shape here, right below it. As we can see here, it's just a slightly different shape. We've basically added an extra depth. So now it's a 3D matrix, even though the last dimension is only one input. There's no magic in regards to that shape. Right here, this shape, it doesn't really matter that we're creating this dimension, because it was a 28 by 28 matrix that we're converting into a 28 by 28 by 1 matrix. We're doing that because you can have more channels or more information than just you know, grayscale color, right? We could have red, green, blue, alpha, infrared. You can go beyond, right? You can have a whole bunch of more dimensions in there. In this case, it's just grayscale, and then convolutional neural networks, they really like to have that third. This is the shape that they like. We don't have to have it in this shape if we're writing our own algorithm, which we can do ourselves. It's nice to just take advantage of the framework. So we are adding a dimension. Now we're gonna print out here our training tests and samples. So we can see that our training data is 60,000 images of 28 by 28 pixels and 1 channel grayscale. This is our training size and this is our test size. So overall there are 70,000 total images that are available to us, and we're going to be training on the first 60,000 and then testing with the last 10,000. So this means that the last 10,000 there, the model will have never seen before, and we're keeping this data separate so that way we can evaluate how good the model can perform on data it's never seen before. And that's the true power of AI, is it's being able to provide you an accurate answer without having ever seen that data before. And finally, we're going to optimize here our output data, which is our targets, our target output, what we're going to optimize towards. This is the, you know, hey, this is number 1, this is number 2, this is number 3. This is our answers, right? The answers that that the AI is going to need to learn for. So it's going to give us, when we run through the first time an image, it's going to give us the wrong answer on the output. That's because it doesn't know anything yet. And so what we're going to do is we're going to take the delta of it, how bad it was wrong, how off it was, and we're going to update the layer weights to be just a little bit closer. So the next time that number runs through, it'll be a little bit closer to the right answer. And what we're doing here on this is we're going to do one hot, I believe. This is where we take all of the labels, or the output targets, which are going to be our digits between 0 and 9, and we're going to turn that into an array of 10, and we're going to mark the label of the position of the digit. So it will look like this. Here we go, like that. So we've got our data here that is going to tell us that 0, 1, 2, 3, 4, 5. For example, this output here is going to be 5. And so that's what this is going to do, is going to convert that into output data that looks like this. So now we have we've taken all of our data, we've prepared it, we put it in the right shape for the model that we're about to build using Keras sequential. Let's build a convolutional neural network model using Keras for image recognition. We'll be using Python, and we've got our sequential model ready to go. What we want to do is add a whole bunch of layers to it, and we'll walk through what each of these means. So first we have our input layer, which is going to be describing what that looks like for our input data. This is important because as we're feeding information into the neural network, the first matrix is only it can only be a certain shape, and it will only be compatible with other shapes that we put into it. So this is a critical step as we're feeding in our 28 by 28 image size. This means that dimension of 28 must align. So essentially that we have a dimension that can match, so that way the matrix multiplication is going to be successful. Otherwise, it just won't match and you can't multiply all the numbers together. It's just how matrix multiplication works. You can only have certain shapes. So this helps us, lets us know what that shape is going to be for the input data. The next layer is the convolutional layer, and this is going to give us the actual parameter weights. And what we're saying is that we want 32 dense matrices. So we can see here in this illustration, each one of these blocks here, these bricks are, and they're colored, that are these rainbow colored here, they are the filters, which are just dense matrices. You can also see it's a 3 by 3, which is the kernel size. And that's what we have here. We said we're going to have 32 of those, which is a lot of dense matrices, and they're going to be 3 by 3 shapes. And the depth is really only related to the batch size of the input. So if we were to map this out and to see how many floating point values are in this one convolutional layer, we'll take our calculator really quick, and we've got a 3 by 3 matrix. So that's 3 by 3, that's gonna be 9, of course, right? So you've got a 9 unit matrix, and there's 32 of those. So times 32, and there'll be 288 parameters in the primary matrix. Now there's an extra component there. There is a bias value that's assigned with each of these each of the matrices. And so that'll be an additional 32 plus 32 for the bias. There should be 320 total floating points just dedicated to that one layer. And if our floating point values are 32-bit, we can multiply that by 32, and that will be 10 kilobytes, or no, yes, 10 kilobytes of data, of memory that we need, which is a pretty small amount these days. It's not a big amount of memory required for this first layer. And we can take a look here at the output of the summary for this model, and we can see it is a 26 by 26 by 32. So 32 filters of 26, which is 320 parameters. And the 26 is related to the output size, right? The output shape. So we're gonna have a model, our input was 28 by 28, the output is gonna be 26 by 26 by 32, because we have 32 filters, and it's 26 because as we are striding across like this, one second, as we're striding across our input data, it can only capture the edges. So it's gonna take that original size and it's gonna shrink it by just a bit. Oh, no, not by a lot. Obviously by, 2 pixels on either side, because you need that in order to capture those. You can take another approach in that window, and then you can do something called padding, and then you can move that, this window here as you're making the multiplications to pad on the outside pixels as well, and this will give you the same output shape, but we don't need to do that. So that's what the output shape is, 26 by 26. And then our activation is ReLU, which is computationally efficient. With an activation function, what you want to do is help it prevent exploding floating point numbers, because you can get really, really big numbers, but you can also get really, really small numbers. And the idea with, sigmoid or tanh is that you want to keep values between 1 and 0, or +1 and -1. And with ReLU, it's 0 to infinity, which can be a problem if your input features are above 1, but we took extra care to prepare our data so that way we don't hit infinity. What we're going to do is we're going to stay, in this range, and ReLU is going to help us. You could use the other activation functions, and they provide a little more control, but they are more computationally expensive. ReLU is super cheap because it's just mostly flow control logic rather than any multiplication or division, which are computationally expensive. So ReLU is a nice option. The next layer here is a pooling layer, and as you can see in a pooling layer, there's no parameters. This is just some basic logic that's going to help reduce the number of units. So you can see here in this example where we have this, say it's a 28 by 28, it's going to reduce that down to something like a 14 by 14. Or basically we're going to reduce the numbers by half. What we want to do is capture all the brightest areas. And that's what it's doing. That's what the max part is. It captures the largest values. And then we add another convolutional layer with even more filters in the same kernel size, because that's the window size. We don't need it to go much bigger than this. In fact, if we shrink it or grow it from a 3 by 3, we will typically see less results. The outcomes will be less. So this is the deep learning part of the deep learning where we basically stack layers here. Then we do another max pooling where we reduce it even further. We flatten it so that way it becomes a simple, instead of a whole bunch of independent matrices, we're going to flatten it into one per input. So if our batch size is, we'll still have a 10, but it'll be a 10 by, so for example here we can see that we've got all these matrices here that look like this, and it's just going to flatten it back down into something that looks more like this, except it's gonna completely flatten it into, instead of essentially a 4D matrix, it's gonna put it into a 2D matrix. So that's what flattening is gonna do, which will help convert into a format that these two layers like, which are 2D matrices. Dropout is gonna forget 50%, which seems like a lot, but this is necessary to reduce overfitting. So what you can do is if you had all possible combinations of input values, you wouldn't need a dropout layer because you'd be able to train a model to learn. However, we don't have enough data, enough compute power to learn everything, but we do have enough compute power to have a statistical probability of most possibilities. So we can train it on a smaller amount of data set instead of an infinite amount of a data set to capture the most meaning. We can reduce, instead of, because it's going to capture the exact data. So for example, here we have the number 2. You can train a model to always detect that that's the number 2 100% of the time, as long as it sees that exact same number 2. But if it's off by a couple of pixels, the model won't be able to do it. And part of making it fuzzy and improving the accuracy overall is by adding a dropout layer. It's a simple approach and it works pretty well. Then we have our output layer, which is going to be a dense matrix the size of the number of numbers, the output classes, the output size, which is 10. And it will look like this up here, for example, where we had our number, this is like a 5. And so this is what we'll be optimizing towards. This is the answer. So we have the input data and we have the answers, and we're going to train a model to converge so it learns those answers. And that's it. It's a pretty straightforward model, and it actually works really, really well. This model.summary, it prints out this segment here where it basically describes all the layers. And you can see that we've got quite a bit of parameters in our layers. So we had our first layer, which seemed pretty small, but then it gets a little bit big, but still not too big. It's actually a pretty decent size. And if we run the model, we get a pretty good output in terms of the results. Before we run the model, we can see here that the total parameter size is about 34,000 or 35,000 parameters, and though each one is a floating point value, and those 34,000 parameters is going to be 136 kilobytes. That's because each parameter has multiple bits associated with it, and it looks around to be 4 bits per parameter. The trainable parameters is simply saying that all parameters are trainable. During back propagation, you can disable some of these layers. For example, these 3 layers, you could say disable during the training process, and it would show up as some layers being untrainable. This is necessary if you're doing transfer learning. In this case, we are training a model from scratch, so we don't have to worry about that. So we've created our convolutional neural network using Keras in a sequential model. We've combined a variety of input patterns to be able to shape the model in a way that's actually a very well performing model. So we've got 3 parameter layers here that will be the primary information holding systems, where the matrices in this case are these convolutional networks here, or the convolutional layers, and a dense layer here. Everything else, all these other things, are just helper algorithms that assist in propagating information through the model. So if we were to print this out, we would only see basically 3 segments of floating point matrices in these 3 layers here. Everything else is just helper layers. Now let's actually train it. Let's see what that looks like if we're going to train it. So this is I got this directly from Karas's Hello World for MNIST dataset, and the batch size is 128, which is a pretty big batch size. However, this helps a lot with generalization. So this means that it's going to take 128 pictures. It's going to line them all up, and it's going to rotate and multiply those into the input layer, and then it's going to run each of those through 32 matrices that are 3 by 3 size, and it will look something along these lines. So we have like maybe 10 images here, but we're going to have 128 with the example provided. And then we're going to run through the entire data set 15 times. So we have 60,000 images, 128 batches. So if with 60,000 images in the training set and 15 epochs, this will be about 4,000 matrix journeys to take the batch of 128, and we're going to move that through 4,000 times per epoch. We're going to set the learning rate to 1 basis point. It's like 1/10% using the Atom optimizer, which is a stochastic gradient descent. So every time a batch is created, it's going to randomize the images. Then we're going to compile and train the model. So the compilation is going to say this is a categorical cross entropy, which means that we have multiple outputs. So like this right here, it looks like this. We are optimizing to be, there's 10 categories. So with this here, that's what we're optimizing for. If it was binary, it would be just 1 value like that, basically just like that. However, we have 10, so we want categorical cross entropy. We're using Atom optimizer, and then we're going to be tracking accuracy with which will be leveraged in the eval function. Here's where the training happens. The model.fit, which is also the model.train function. It's going to take your image data, which is the xtrain. It's like these are the images, right? The 28 by 28 pixel snapshots of numbers, and then the train is going to be values between 0 and 9, which are the actual numbers, but it's going to be in this format right here. So basically we have the images, we have the targets, and we want to the AI function to optimize to be able to find the answers between the two. We're going to pass in our hyperparameters here, epochs, batch size, and then the validation split, which is, it says 10, I believe this says 10%, right? Because we've taken our test, but I think we did a little more than 10%. So this is off by a little bit, but so this function right here in line 72, 73, and 74 is going to take a long time. It'll take a while because it has to run through those batches 4,000 times the number of epochs, which is a lot. So if we run it, it looks like this. Each epoch took about 10-15 seconds on my laptop here, and we got to 15 epochs. Each epoch, it will evaluate the accuracy test data that we've set aside. So you can see immediately after the first epoch, it's already 98% correct, which is really interesting. And then each additional step, each additional epoch is only ever so incrementally making it better, right? So we have right around 97.9%, 98.6, 98.8, 98.9, and then we keep going and we get to 99, and it's just ever so slightly better each time. If 99% is really good, that's great. That means, although there is a downside of like 1 out of every 100 are technically going to be wrong. So it is really nice to have the computer be able to do all that data analysis for us really quickly, and a human doesn't have to do it. Even if it's wrong 1 out of 100 times, a human will still be wrong at a certain set interval as well. So this is a neat trade-off, right? We can take advantage of an AI or a computer to do a lot of the heavy lifting and a lot of big bulk work for us really quickly without any we don't need any human help. Now the trade-off is a little bit of accuracy loss potentially, depending on what a human's error rate would be. A human's error rate could actually be worse than this. They could be wrong 6 out of 100 times. So in this case, the AI model is far superior. We can go a step further and improve this accuracy even more, tuning and tweaking the model parameters. So we might want to add more weights. We can change what the dropout looks like. We can add some more layers. Instead of using ReLU, we could use a different activation function. We could capture more data. We can convert some of the image data to slightly rotate some of the images or skew some of the images to increase the pool of our overall training data. We can do a lot of things to increase the overall accuracy of the model. However, 99% is really good. So we did it. We built an image recognition machine learning technology using Python and Keras. Even though it seems complicated, because it is a little bit, however, it's really straightforward when we just understand we are just dealing with matrices. That's it, just floating point numbers. And we're configuring how we interact with those matrices all through matrix multiplication, in which order and in what shape, and what information in each of those matrices that we're pulling out, and as we're passing it through additional layers, additional matrices. That's it. It really is all that. And so there's just a bunch of patterns and strategies on how we leverage those matrices and which algorithms we apply to each one of those floating point values inside of the matrix. And as we tune overall in time, we will improve the quality and the performance of those matrix. Matrix multiplications are expensive. However, we can use multiple CPUs or GPUs, right, multiple cores, to run those math applications for us, right? We need those operations to be parallelized as much as possible, which will dramatically increase the speed of the model. And so then we can increase the number of weights or the number of parameters, more floating point numbers, bigger matrices, and that will allow us to provide more data in those matrices. However, at a certain point, we're going to have a matrix that's offset, right? Or it's tilted in one direction, where a lot of the knowledge might be in the left side of the matrix, or one side or the other. And so in order to take advantage of more model weights, we have to find ways to smoothen that information out so we capture more of the meaning and we can spread that knowledge across more of those floating point numbers. So that's it. We're just taking the strategies of those matrices, multiplying them against each other, and getting a final output.